Well, welcome everyone. It's a pleasure to welcome Federica Fanoni, who is going to talk about isospectral hyperbolic surfaces of infinite genus. So thank you, Federica.
Oh, thanks for the introduction and the invitation. Very happy to be giving a talk here. Too bad I've never actually been to Durham. Hope to fix that soon.
Yes.
So the talk is about hyperbolic surfaces and especially isospectrality. So it's going to be length isospectrality. And the new results are about surfaces of infinite genus. But I'm going to start with just a general introduction, talk a bit what happens with finite type surfaces, and then to see what the difference is in the case of surfaces of infinite genus. Just do stop me at any point if there's something that I'm not defining that I should. Okay, so hyperbolic surface, X for me is always going to be a hyperbolic surface. So it's a surface with a Riemannian metric of constant curvature -1. Metric. Constant curvature -1, or if you prefer something that's locally isometric to the hyperbolic plane. And I'm going to ask that the surface has no boundary. I'm also going to ask that it's complete, geodesically complete, so each geodesic can be extended infinitely long. And the third thing is more of a technical condition that's not very important if you don't know what it is, but for the results to be stated, to be correct, I need to put it. It says that it's equal to its convex core. So for surfaces of finite type, we're going to see soon that essentially means that if there's points that are removed around that, the structure is that of a cusp. But again, it's more of a technical condition. It's not super important for understanding what happens in the talk. So given a hyperbolic surface, something one looks in hyperbolic surfaces is geodesics, closed geodesics in particular, and the length spectrum collects the lengths of all of these. So the length spectrum is a collection of lengths of gamma, where gamma is any primitive closed geodesic. And primitive just mean that it's not the same geodesics that have gone around multiple times. So it's not the iterate of some closed geodesic. It's not very important that either, but. And I'm going to consider this set actually with multiplicities, meaning that if I have multiple curves with the same length, I'm going to remember how many times that length appears. On the other hand, I don't remember in this set if I have a length to which curve it's associated. So it's an unmarked length spectrum. So this thing is going to be actually a multi-set. And it's a multi-set that captures a lot of information of the surface. And we say the two surfaces are isospectral if they have the same length spectrum, again, as multi-sets. Just an extra piece of notation, I'm going to denote by I of x the collection of all surfaces that are isospectral to x. So all the y isospectral to x with the same length spectrum. I'm going to consider that up to isometry. So it's clear that two surfaces that are isometric are going to have the same length spectrum. And the question is somehow to which extent is the converse true? So more generally, to which extent does the length spectrum determine the surface? To which extent does the length spectrum determine x? So if I give you a set that I know is the length spectrum of something, can you tell me what's the surface I was starting with? And actually, at first, it was conjectured that, yes, you could tell it entirely up to isometry. So this was a conjecture by Gelfand. That actually, if I know the length spectrum, I know the surface up to isometry. Determines X up to isometry. And it turned out that's actually not true. And there's been lots of constructions to show that this was not the case. So I would like to talk a bit about what is known in the case of surfaces of finite type. So finite type surfaces are those whose fundamental group is finitely generated. So in practice, that means for the condition that I have, that my surface is going to have a closed surface of genus G to which I've removed n points, where both G and n are finite. And as I was saying before, so this will be endowed with a hyperbolic structure. And as I was saying before, the fact that I'm asking that the surface is equal to its convex score means that if I look around one of the points that I've removed, I have a very specific structure, meaning there's a little area around it that is given as follows. So here, this is a picture of the upper half plane, so which is a model for the hyperbolic plane. So H2 is the collection of points of positive imaginary part. And I can look at the subset where the imaginary part is at least 1. This is the part that's shaded in blue. And there's an isometry of the plane, which is the map that maps Z to Z plus 1, which keeps this set fixed. And if I quotient that down, what I get, well, topologically, I get a cylinder. But geometrically, it looks more like this, in the sense that there's some definite length at the base, and then the length becomes shorter and shorter as I go up. So what I get is a finite area cylinder. Which is what we call a cusp. And the point is, for the surfaces I'm considering, if I have a point removed around it, I have exactly this structure. Okay, so what's important to know about these that probably most of you know, but I'm just going to recall it. So if I fix S a topological surface of signature Gn, so with genus G and n points removed, I can look at the moduli space of S, which is just the collection of all hyperbolic surfaces of this topological type up to isometry. So it's a collection of X hyperbolic surface homeomorphic to S up to isometry. And the important thing to know here is that this moduli space is big, meaning, so it's not a manifold, is what it's called an orbifold. So there's some points in which I don't really have a manifold structure, but it's rather the quotient of a manifold by a finite, but it looks rather like the quotient of a manifold by a finite group. It's not super important, but it's something of dimension 6G minus 6 plus 2n. Again, the explicit dimension is not important. What it means is that if I fix the topological surface, I have many, uncountably many hyperbolic structure on that given surface. And an extra thing, what one can look at is also what is called Teichmüller space, which you've also maybe heard. So this is also a parameter space of hyperbolic surfaces. It's a parameter space of marked hyperbolic surfaces, which essentially means that I kind of record an identification with the base surface S. It's not super important. It's a hyperbolic surface with an extra structure. It's an equivalence relation that's a bit weaker than isometry. And this turns out to be the universal cover of moduli space, and it's something that's homeomorphic to 6G minus 6 plus 2n. Okay, this should be everything we need about hyperbolic surfaces. Let's go back to talk about their length spectrum. So the first thing that the first thing I would like to remark is that what is known is that if I now I'm going to say everything I'm going to say at the moment is for finite type surfaces. What is known is that the length spectrum is discrete. So what does that mean? This means that if I take any positive constant and I look at the collection of curves of primitive closed geodesics whose length is at most L, that is, I look at all the elements in the length spectrum of that are at most L, then this set is finite. Okay, so there's always finitely many, and there's something that's actually important in the proofs of many results of the results that I'm going to mention later on. So the first thing one can say, so the question was, to which extent does the length spectrum determine the surface? And the first thing that we can say, which is due to Huber in the case of closed surfaces and Müller in the case of surfaces with cusps, is the following. So the length spectrum determines the topology. So that means that if I am given the length spectrum, I know the genus and the number of punctures on my surface. In particular, that means that if I have a surface in some moduli space, then I of x, which was the collection of all surfaces that are isospectral to my given surface, that is contained in the same moduli space. But I just spent a lot of time telling you that this moduli space is very big. So far, yes, the length spectrum does determine the surface up to a certain point, but so far we still have uncountably many possibilities. And the fact is that actually we can do much better. And this is the next result, due again to McKean in the case of closed surfaces and Müller in the case of surfaces with cusps, which is that for any finite type surface, if I look at the size of isospectral families, this is always finite. So I want to think of that as saying that the length spectrum determines the surface up to finite error. So maybe I cannot tell you precisely which surface I have, but I can give you a finite list of surfaces, and I know that the surface you start with is one of them. Even more, in a sense, is true. This is still, in a sense, going in the direction of the conjecture of Gelfand. So what Wolpert studied is the following. I fix a topological surface, and I look at all the surfaces of that topological type that are not determined by the length spectrum. So this essentially means that X is not determined by the length spectrum because there's some other surface that's not isometric to it, which is isospectral. And what Wolpert showed is that in the case of a closed surface of genus G, and then this thing is a proper real analytic subvariety of Teichmüller space. So this is a very nice result. But the main thing I want to take out of this is that this means this is a positive codimension space. So this is telling me that in a sense, a generic surface is determined by its length spectrum. So if X generic outside of something of positive codimension is determined by its length spectrum. Okay, so this was still at the point, I think, when people didn't know that Gelfand's conjecture was false. And roughly at the same time, there were the first examples of hyperbolic surfaces that were non-isometric and isospectral to each other. And the first, I think, were due to Vignera. And then there's been lots of constructions. So something I'd like to mention here is a combination of results of Boozer and Brooks and Se, which tell you that if you have genus at least 4, and you look at the dimension of this subspace constructed by Wolpert, this is actually positive. So what's telling you is that there's actually plenty of hyperbolic surfaces that are not uniquely determined by their length spectrum. So it's not just a few isolated points, but there's really families of such surfaces. Okay, so well, this is the first example, the first thing I'm writing down that actually shows that Gelfand conjecture is false. Something I said is that the size of an isospectral family is finite. So we can wonder if there's bounds on this, and work on finding bounds of this has also been done. So here the results I'm going to mention are all for closed surfaces. I think they can all be pushed to the case of surfaces with punctures, but they were not explicitly written down in that setup. So just to be sure, I'm going to write everything for closed surfaces. So if I have a closed surface of genus G, what Boozer proved, is that the size, the number of, there's a bound on the number of surfaces that are isospectral to it that depends only on the genus. So I think what he showed is that this is at most e to the 720 g squared. It's not super important what the function is. What's telling me here is that what's important here is that this is a bound depending on the topology, depending only on the topology. So that means that if I have any two surfaces in the same moduli space, there's a uniform upper bound to how many other surfaces can be isospectral to either of them. And this was actually improved much more recently by Perlier. He proved that this can be brought down to something of the form G to the AG, where A is some explicit positive constant. So you could wonder if it's important actually to have a dependence on the genus. Maybe there's a global upper bound that does not depend on the genus. And this is not the case. So if the genus grows, isospectral families can become bigger and bigger. There's been plenty of constructions. I would like to mention what the best one is. This is due to Brooks, Cornet, and Gustafsson. So what they showed is that there exists some sequence of genera going to infinity. And for each genus, I can find a surface, a hyperbolic surface of genus GK, such that this is actually in a large isospectral family. So it has something of the form GK to the power B log GK for some B, some fixed positive B. So this means there's no global upper bound that does not depend on the topology. At the same time, of course, so this is the best known upper bound for as far as I know, and this is the best known construction. So there's still a difference in between these two bounds, and we don't know whether either of the two is correct, whether either of the two can be improved. Okay, so this was a short version of what's known about finite type surfaces. Essentially, what I wanted to say is finite type surfaces, a surface is generically determined by its length spectrum, and when it isn't, there's an upper bound depending on the topology on the size of the error, let's say. Okay, So as the title was saying, what I'm interested in today is surfaces of infinite genus. These are examples of surfaces of infinite type. So let me tell you a little bit about those. These are surfaces whose fundamental group is not finitely generated. So here's some examples. I can look at the first, in which I have an infinite genus thing, where the genus goes to infinity only in one direction. In the example on the top right, I also have infinite genus, but genus goes to infinity in 3 different directions. So these 2 surfaces are actually not the same topologically. And then I can do more complicated things. I can also remove points, and I can remove finitely many, but also infinitely many points. So here, for instance, I have an example in which the idea is that I have infinitely many of these chimneys that go off to infinity. And so I will also have 2 other ways of going to infinity following this right and left direction. And I've also removed infinitely many points. The idea, I've removed 1 point for each of these chimneys. And the last example that I have here, here I'm taking a torus, and what I can remove is, for instance, a Cantor set. Okay, so these are some examples of surfaces of infinite genus, and when I say some, it's really a few, in the sense that there's uncountably many topological types of surfaces of infinite type. So these are really just a few examples. Something that's important to look at when you look at surfaces of infinite type is to look at ends, which I've already a bit hinted at. So ends, I don't want to define them precisely, but they are ways of going to infinity, of leaving every compact. So going to infinity here means leaving every compact. So in the examples above, essentially all the arrows that I've drawn are ends. I can leave every compact by going all the way to the right in the first example, or in one of these 3 directions in the next one. In the picture below, each of these puncture is also an end, since they leave every compact by getting closer and closer to each of these points. In the same spirit, in the last surface, I have a Cantor set of ends. So each of the points of the Cantor set is going to be an end. And something else that one can say about ends is that there's 2 types. These are planar or non-planar. And planar ends are those that have a neighborhood which does not have any genus. So here these are, so with a neighborhood, with a genus 0 neighborhood. So in the examples above, in the first and in the second surface, the ones on top, the ends are non-planar, because for as far as I go, I will always see genus. While in the examples below, I have a bunch of non-planar ends, so all of these are non-planar ends. I can take a little neighborhood around it, and I don't see any genus, and the same thing for every point in this Cantor set. Can take a little neighborhood that does not contain any genus. And ends are actually organized in a topological space, so that I'm going to denote by ends of S. This is the space of ends. Since I haven't defined ends properly, I cannot really tell you what the topology is, but it's what you can imagine. So in the sense that, for instance, in the last example, the topology is that of a Cantor set. And in the example So in the example just before, I have these two ends, this one and this one. And then I have these sequences of ends here that are actually converging to the two ends. And at the same time, all these punctures are also converging to the two ends. And you can think about it like if you have a neighborhood of this end, you will always see infinitely many ends of infinitely many ends above and infinitely many punctures. So this is going to give you sequences converging to it. Okay. So something that one can say is that every infinite type surface admits a hyperbolic structure. So what I actually didn't say before is that for finite type surfaces, you need the Euler characteristic to be negative to have a hyperbolic structure. Here, the Euler characteristic is almost like if it were minus infinity all the time. So they all admit a hyperbolic structure. And they actually admit plenty. Just as before, we have very large deformation spaces of hyperbolic structures. And yeah, there's not a lot that's known about the length spectrum. But what is not that hard to see, if you know a little bit of hyperbolic geometry, is that in general, the length spectrum is not discrete. So remind you, discrete meant that there were only finitely many lengths, finitely many curves of length with at most some constant L. And it's not that hard to show that this is not the case here. So let me just give you an idea. So in hyperbolic surfaces, what people look at very often is what are called Panzer compositions. These are a collection of curves that cut the surface into three-hole spheres. And the point is, if you fix the lengths of these curves, the topology of the geometry of the three-hole sphere is fixed. So this is a basic fact of hyperbolic geometry. If you have a three-hole sphere and you know the boundary lengths, you know the hyperbolic structure in each piece. And then the only thing you need to know to actually know the hyperbolic structure on the full surface is how you glue these pieces. So you actually have an extra parameter, which is called the twist parameter. But what this is telling us is that in particular for these curves that I've drawn, I can choose, so I can get a hyperbolic structure on this surface by fixing the lengths of these curves as I want them. So in particular, I can choose the length of all of these curves to be some fixed epsilon. So I have infinitely many curves that have a length bounded above by, say, 1, whatever. So in general, hyperbolic surfaces of infinite type won't have a discrete length spectrum, and this is quite a difference from what happens in the case of finite type surfaces. And it's actually, in a sense, much harder to construct something where the length spectrum is discrete. And there has been some work on that. This is work by Basmajian and Kim. So what they do is that they can give conditions on to have for X to have a discrete length spectrum. And using this, they can actually construct large families of surfaces, either with discrete length spectrum or all with non-discrete length spectrum. So infinite dimensional families. Of hyperbolic surfaces with discrete length spectrum, or also all with non-discrete. length spectrum. But for as far as I know, this is the only thing that's known for the length spectrum of infinite type surfaces. There's something else that's known in the case of the simple length spectrum, where you look only at simple closed curves, simple closed geodesics. But that's quite a different story. So let me tell you what I could prove. So I got these two results. So the first one is for surfaces that have infinite genus and that have no planar ends. So I have no points removed, essentially. Then I can find, for every n, I can find a hyperbolic structure on my surface that has at least, well, n-1 other hyperbolic structures that are isometric to it, that are isospectral to it and not isometric to it. So I can find these large isospectral families. So in particular, this tells me that, so in the finite type case, I knew that there was an upper bound on the size of isospectral family that depended on the topology of the surface. Here I cannot do that. I can find arbitrarily large families. So there is no upper bound on the size of an isospectral family, depending only on the topology. This is the first difference. And something else I'd like to mention, it's not very important, but actually I can prove more in the sense that I can prove that these surfaces fit in infinite dimensional families. So there's actually infinite dimensional families of such surfaces. Meaning that in a sense, I have infinitely many directions in the parameter space of hyperbolic structures to deform my surface X and still get hyperbolic structures with large isospectral families. The second result requires a slightly different condition on the topology of the surface. So this, I require again infinite genus, and I require that the space of ends is self-similar. I'm going to tell you in a second what that means, but for now, just think of it as an extra condition on the topology of the surface. Then what we actually can show is that there's a hyperbolic structure whose isospectral family is not only not finite, but is uncountable. So a couple of remarks. The first one is that as above, actually, I can get infinite dimensional families of such surfaces. And the second is that, so for those who know what that means, is that actually I can show that uncountably many Y in this family are not quasi-conformal to each other. So for those who don't know what that means, I didn't want to define quasi-conformality, but it can be thought in a sense as a weakening of being in a quasi-conformal map is somehow something that's weaker than an isometry. So an isometry is a most quasi-conformal map, and quasi-conformal are in a sense a relaxation of isometries. And what this is telling me is that in a sense, Gelfand's conjecture in this case really fails to a much larger extent than in the case of surfaces of finite type. Okay, all right, so what I wanted to do next is talk about what the self-similarity condition is and a bit about the tools of the proof. But before I go on, is there any question about what I've said so far? Okay, maybe later. So let me tell you this self-similarity condition. It's not super important to know the precise definition. I'm going to give it in the case of surfaces without planar ends. Oops. Because it gets a bit easier. So I told you that the space of ends is a topological space. Self-similarity is a topological property of that. So it's telling me that every time, then I can write my end space as a union of two disjoint sets, U1 and U2, which are both closed and open. Then I can find a copy of the entire end space in at least one of the two. So there exists I, and there exists an open subset A, which is homeomorphic to the full space. It's maybe a bit obscure, so let me just give you a couple of examples that hopefully clarify what that means. So the first example here is a surface that has a single end. So here the space of end is a single point. It's going to infinity in this direction.
So Federica, I guess you probably mean U1 and U2 are non-empty as well.
I mean for every decomposition. So
for every decomposition. Okay, yeah.
But yeah, if it's empty, it's so indeed in the first case, I don't have a non-trivial decomposition, and the end space is 1 point, so I can only decompose it in 1 point and the empty set. So it trivially satisfies this condition. And the second case is actually more interesting. So what I've taken here, this thing here is an infinite trivalent tree. And you maybe know that such a tree has an end space, and this end space is a Cantor set. So what I've done then is that you can essentially take a thickening of that in R3, and then put genus at each vertex. So this gives me a surface of infinite genus, and the space of ends is going to be a Cantor set. So here the self-similarity is the self-similarity of a Cantor set. In the sense that if I have a Cantor set, I know that if I split it into two pieces that are closed and open, they're both going to be Cantor sets. So in that case, again, it's satisfied in a very easy way, because if I split the space of ends into two pieces, each of them is going to be homeomorphic to the full space. And so now it might seem like a pretty restrictive condition, and it isn't, in the sense that there's uncountably many topological types of surfaces with this property. There are uncountably many homeomorphism type of S with self-similar end space. So the second theorem does apply to actually quite a lot of surfaces. A couple of non-examples here in these two cases, the space of ends has cardinality in the first case 2 and in the second case 3. So in both cases, the topology is just the discrete topology, that the space of ends is 2 points here and 3 points here. So if I split it into a non-trivial, if I have a non-trivial decomposition of that, I will never be able to find a copy of the entire set in any subset. So these surfaces won't have the property of having a self-similar end space. Okay. That said, let me give you some ideas of how one proves such a theorem. So if you know anything about isospectrality, you won't be surprised at the fact that the first tool is a result of Tsunada, which is the following. So this actually works, I'm stating it here for hyperbolic surfaces, but it works for much more general manifolds. So I pick a hyperbolic surface and I have a finite group of isometries of that surface. I assume that that group has finitely many fixed points. And I pick two subgroups of that group and I assume that they are almost conjugate, which is I'm going to tell you the definition of in a minute. And I assume that they act freely on X. Then I can look at the quotients, X modulo H1 and X modulo H2. These are surfaces because they are a subgroup of the isometry group that act freely. So I can look at their length spectrum. And what Tsunada tells you is that the surfaces you get are isospectral. The two length spectra are the same. What Tsunada does not tell you is that the two surfaces are different in the sense that they are not isometric. So not known if H mod H1 and X mod H2 are isometric or not. And in general, they can be. So something you need to check when you apply this tool to find isospectral surfaces is to then check that the surfaces are not isometric. So what's the definition of almost conjugate? It's a relatively simple condition. If I look at any element of the group, I can look at the conjugacy class of G.
Maybe a quick question.
Sure.
If H1 and H2 would be conjugate,
yeah,
could you then conclude that they are isometric or not?
Precisely. So the important thing is going to be that that you choose almost conjugate but not conjugate subgroups.
Thank you.
And then you can start hoping that they are not isometric. Yeah. So if you look at here, this is the conjugacy class of G, of little g in big G. And I can intersect it with H1 and with H2. And what the condition is that these two sets have the same cardinality. So I'm starting with finite groups, so this makes sense. So what I'm asking is these two have the same cardinality. And indeed, as we were saying, so it's not hard to check that if you are conjugate, then you are almost conjugate. But precisely as the question was asking, here, if I have conjugate subgroups, I'm going to get isometric quotients. So what's important is that there are examples of things that are almost conjugate but not conjugate, and that's gonna give you a way of to construct isospectral non-isometric surfaces. So the second tool is a much more recent work that allows me to apply this result. So this is a result by Auga, Patel, and Flames. The result is actually much more general, but this is the part that I need. So I take a surface of infinite genus without planar ends. This is the same condition as my theorem A. And I fix any finite group. Then what they show is that I can choose a hyperbolic structure on the surface such that the isometry group is exactly this group. So this kind of comes, so the idea comes from work of Alcock. So what Alcock did is give a different proof of the fact that if G is any countable group, then there exists a hyperbolic surface X with isometry group again equal to G. And the idea is essentially the following. So I look at the Cayley graph of G with G as generating set. So this means that the vertices correspond to elements of my group, and I have oriented edges with labels. So the oriented edge with the edge with label H goes from an element G to a vertex label G to a vertex label GH. And what essentially Alcock does is to choose vertex surfaces to put at each vertex and edge surfaces to glue in between, and do it in such a way that you are sure that there's no extra isometries. It's not hard to show that you can get it. You can make it so that G is a subgroup of isometries. You need to be sure that there's no more. But what he does, so what this construction does is give you a hyperbolic surface with this property, but you don't know the topology of that surface. And what Augap, Patel, and Flamis do is to pick this idea and make it considerably more complicated to be able to fix the topology of the surface up front. So that when you do this construction, you actually get a hyperbolic surface with a specific topology. Okay, so with this in mind, I can give you an idea of how we prove the first theorem. So the first theorem was under these conditions, which are the same as the last theorem that I mentioned. I can find large isospectral families. So what do? I fix the topological surface. I fix N, and I choose actually a specific G finite and specific subgroups H1 and H2 that are almost conjugate and not conjugate. And then what I look is actually the nth power of these. So the product of G, of n copies of G. And I have some obvious subgroups that I can construct using H1 and H2. So I can pick, for each component, I can pick H1 and H2. So if phi is a map from 1n to 1, 2, I can look at H phi, which is the subgroup where I pick H1 or H2 as the map tells me. So this gives me a collection. So all of these where phi varies. These are 2 to the n subgroups. And they are, it's not hard to show that they are again almost conjugate and not conjugate in G to the n. So almost conjugate, that's the important part. So now I can use the construction of Augap, Patel, and Flamis and get a hyperbolic structure Y, hyperbolic structure on S with isometry group G to the n. And then, well, the magic of the construction is that if I look at the quotients by all of these subgroups, they are all going to be homeomorphic to S. And Tsunada tells me that, so these are 2 to the n surfaces. And what Tsunada tells me is that they are isospectral. And what we need to check is that they are actually pairwise non-isometric. And this is maybe where the hardest bit of the work goes. And this really needs the construction of Augap, Patel, and Flamis. So I didn't want to go into the details of that. Yeah, so this is essentially how the theorem works, how the first theorem works. What happens in the second theorem is that there I need much more groups. So instead of, because I need to find an uncountable family. Instead of looking at G to the n, I look at the product of infinitely many copies of G. And I similarly look at subgroups constructed in a similar way. And then I won't be able to apply directly Tsunada's criterion because that works only for finite groups. But luckily, there's an alternative proof that was discovered first by Buser and then made more precise, maybe by Berard. This is called transplantation of geodesics that can be applied to this setup, and this is going to give me candidate surfaces that then I need to check are not pairwise isometric, and actually most of them are also not quasi-conformal to each other. And I think it's a good moment to stop, so thank you for the attention.